welcome to the first video in the CH1601 series. My name is Luke Stewart and I'm a previous CH1601 student. In these videos, I'm aiming to cover the main concepts of the course. These videos will vary in length, depending on the topic, but I will generally aim to limit their length as much as possible. So what is organic chemistry? It's the study of structure and reactions of compounds, which usually include carbon, hydrogen, oxygen, nitrogen, and sulfur, for example. Understanding structure is extremely important for organic chemists because this allows us to identify the chemical groups within the compound and understand how they can be put together. Of course, the specific structure of an organic compound gives rise to specific functions, for example, medicines in the pharmaceutical industry. A basic principle to understand in organic chemistry is the hydrocarbon framework. This is essentially the backbone of the molecule. From this hydrocarbon chain, various functional groups can be added. The functional groups form the reactive part of the organic compound. Firstly, let's look at linear hydrocarbon chains. These hydrocarbon chains all have different names depending on the number of carbon atoms in the chain. One carbon atom is methane, 2 carbon atoms, ethane, 3 carbon atoms, propane, 4 carbon atoms, butane, 5 carbon atoms, pentane, and 6 carbon atoms, hexane. Of course, we are drawing these structures on paper, so we need to find a way to represent their 3D structure. Let's take methane as an example. Here we have a carbon atom with 4 hydrogen atoms attached. We can rotate the structure and we see that the hydrogens are equally spaced around the edges of the carbon at angles of 109.5 degrees. In this orientation, we see the compound has 2 hydrogens in the same plane, 1 hydrogen pointing out of the plane, and 1 hydrogen pointing into the plane. On paper, this translates to this drawing. Moving on to larger hydrocarbons, such as butane, we can draw the 3D arrangement of atoms as depicted here. But for larger molecules, drawing out all the carbon and hydrogen atoms can be quite time-consuming. Therefore, to simplify things, we use zigzag chains instead. It is also possible for hydrocarbons to come in a ring structure. To name these compounds, we simply add the prefix cyclo in front of the alkane name. For example, here we have cyclohexane, which we can draw in the 3D format as shown here, or in the shortened version as shown here. One important point to note is that the smallest ring structure possible is cyclopropane, with 3 carbon atoms. It is not possible to make a ring with methane, 1 carbon atom, or ethane, 2 carbon atoms. A special type of hydrocarbon ring is benzene with formula CH1601. This is an unusual type of structure which has electrons delocalized across the ring. We often represent this as alternating carbon-carbon double bonds and carbon-carbon single bonds. On paper, we draw benzene like this, but sometimes it can also be represented like this with a circle in the middle to demonstrate the delocalized electrons. If we have a benzene ring attached to a larger molecule, we also represent the ring as pH, which saves time and effort on your behalf. Now we're going to talk about the more exciting and reactive parts of compounds. These are called the functional groups. To prove that these exist in 3D space, I'm using model kits. To start off, we can have alcohol groups, which contain 1 oxygen atom. We tend to draw alcohols like this on paper. Or we can have carboxylic acids, which contain 2 oxygen atoms. These compounds are drawn like this. When carboxylic acids and alcohol groups react together, we get ester compounds, as shown here. On paper, we draw it like this. We can also have compounds which contain nitrogen groups. For example, amines contain the amino group, which consists of 1 nitrogen and 2 hydrogen atoms. If we react an amine with a carboxylic acid, as shown before, we can obtain an amide functional group. There are various functional groups which you will be required to know. for CH1601. A full list is provided here. When it comes to functional groups, this adds another level of complexity when naming compounds. Going along a hydrocarbon chain, it is important to place the functional group on the lowest carbon number. For example, in this amine molecule, we would call the compound 2-aminopentane rather than 4-aminopentane. If we move the amino group to the end of the carbon chain, this time we would name the compound 1-aminopentane. In some textbooks, the compound may be called pentylamine because we have a C5H11 pentyl group attached to the NH2 amino group. When you compare the chemical formulae for 2-aminopentane and 1-aminopentane, you see that they are the same. These compounds are called isomers. They have the same chemical formula, but different chemical structures. Isomerism is an important concept to understand. To give you another example, let's take C4H10. At first you may think this is a straight-chain butane molecule. However, we can also have branched hydrocarbons, for example 2-methylpropane. This brings a close to the first CH1601 video on naming compounds and isomerism. To test your knowledge, try the quiz now.